Welcome back. So, in the last lecture we just talked about the consolidation, fundamental of consolidation in soil, and there we have seen and we have discussed what is consolidation and how the consolidation happens in soil, right. So, basically consolidation is nothing but the expulsion of water or the drainage of water through the pore, from the void space of the soil matrix and causing some deformation or the volume change in the soil matrix or the soil deposit. So, in the last lecture we just talked about or we just discussed about this problem. Say suppose you have some sand layer at the top and another sand layer at the bottom, and in between you have the clay layer which is getting sandwiched between these two sand layers and which is having say depth h. So, because sand, you know, from the permeability point of view, the sand is a good draining material, right. I mean that means the water will be passing through the sand deposit very easily, right. So, water basically if you apply the stress on this clay deposit, basically the water will try to drain out through this interface of sand and clay, right, because clay or sand will facilitate the drainage. Now, in this problem basically we applied some external increment of stress, that is delta sigma. So, the some externally applied load or the load intensity is getting applied on top of the sand layer, and the groundwater table is here. So, the clay is completely saturated. So, there is no issue for that. So, we are not considering any partially saturated or unsaturated soil. So, clay is completely saturated. Now, what will happen? So, once you apply the load immediately at T equal to 0, we have seen this is my total stress increase, because total stress increase will be remaining same, because you are not going to change the stress increase during the say process, right. So, delta sigma will be remaining same. So, therefore, your total stress increase will be always same as delta sigma, whereas you will be having some say balance in the pore water pressure built up as well as the effective stress enhancement, right. So, so this at T equal to 0. So, your total stress is delta sigma, and as we have discussed in the last lecture that immediately you apply the load, the whole load will be taken care of by the water or the pore fluid, right, because the drainage is not happening and water is incompressible. So, it will take care of the whole load, because it will not transfer anything to the soil solid. So, therefore, your pore water pressure will be equal to your stress increase, that is delta sigma. So, delta U is equal to delta sigma, whereas your effective stress, right, effective stress delta sigma prime will be 0, because the whole load whatever you have applied externally, the whole load will be taken care of by the water. So, nothing is getting transferred to the soil solid. So, therefore, there is no enhancement or the increase in the effective stress. So, at some time say at T greater than 0 and less than infinity, then slowly what will happen, the water will try to drain out from the clay deposit, because it has got some drainage path through the sand layer at the top as well as the bottom, as I told you. So, the water will try to dissipate or try to drain out from the clay deposit. So, therefore, at greater time, so what will happen, the pore water pressure will be gradually decreasing and the same amount of effective stress will be getting enhanced, right. So, you can see, so you will be getting simply 0 pore water pressure at the interface, because that is that location is the closest location or the nearest location to the drainage path, right. So, that is why the pore water pressure immediately pore water pressure will be getting dissipated at those locations, right, at top as well as the bottom, and it will be remaining maximum at the middle, because the middle water particle has to move either on towards the top or towards the bottom to drain out from the clay deposit. So, the gradually the pore water pressure will be getting reduced, whereas the same amount of effective stress will be getting increased, right. So, that is the effective stress diagram. So, at T greater than 0 less than infinity. Now, if T is infinity, now you have allowed sufficient time to drain out the water, then what will happen, the total stress increase will be remaining same as I told you, because you are not increasing the externally applied load. So, what will be the pore water pressure, because at T equal to infinity the whole whatever water was under pressure. So, that has gone out. So, that has drained out. Okay. So, your pore water pressure will be completely dissipated and pore water pressure will be simply equal to 0. So, now the what will be taking the total stress then. So, whatever stress increment you have given, the whole stress will be taken care of by the soil solid. That means, effective stress will be increased by the same amount. So, your effective stress delta sigma prime is equal to delta sigma. So, this is happening with respect to time. So, as you vary the time, you are getting different phenomena. So, initially the pore water pressure will be the maximum and slowly it will be decreasing and finally it will be becoming 0, whereas you will be getting the reverse trend, that is in the effective stress, that is the effective stress was 0 initially and gradually it will be building up and then finally it will be becoming maximum. I hope that you have understood the phenomena, right. Now, with this concept we can talk more about the consolidation and we will be developing the consolidation equations, expressions and the theory. Okay. Now, one dimensional lab consolidation test. So, first we will see that how we can perform the laboratory experiment to understand the consolidation phenomena in soil. So, this is typical say laboratory experiment setup, that is consolidometer. So, here what we have, you have some ring. So, some metal ring. So, that is this is a cross section, whatever you are seeing on the figure, that is the cross section of the test setup. So, this is the ring, okay. It will be having all round means say cylindrical say confinement, okay. The soil specimen will be placed inside the ring. On top of the soil specimen, you will be putting the porous stone to facilitate the drainage, because porous stone will allow the water to come out, but it will not allow the soil particles to dislocate from one place to another place, right. So, the porous stone will be facilitating the drainage. So, now what you will do, you will apply some load, okay, and this whole setup will be completely saturated, that means it will be submerged under water, right. So, now you will be applying some load, externally applied load on top of this porous stone, okay, through some mechanism, loading mechanism, and then you will be observing the deformation. That is, the deformation means because you have the confinement in the lateral direction. So, the soil will be allowed only to deform in the vertical direction. So, the volume change whatever you are considering, that volume change is nothing but equal to the change in depth of soil specimen, because you do not have any change in the diameter. So, diameter is completely confined, the soil specimen will be only deforming in the vertically downward direction, right. So, the whatever volume change you are observing in the soil, so that is nothing but equal to the change in height or the depth of the soil specimen, am I right. So, I hope that you have understood the laboratory experiment concept. So, now in this basically we are applying some load, right, on top of this, and we are observing some height deformation or the reduction in height, right. So, delta H. So, these two things we are observing, and then based on that we will be developing the theory, and we can find out that after certain time what will be the deformation, or at different stress increment what will be the deformation. So, this phenomenon is very important, right, for designing any kind of structure on the clay deposit or the saturated clay deposit, because you want to know, say, if I apply or if I construct some building, right, on top of some clay layer, you want to know that how much will be the settlement of the foundation, the consolidation settlement rather, how much will be the consolidation settlement of the foundation. That means, you are applying some you are constructing some building. So, that will apply some externally applied load, and after say 10 years or 12 years or 20 years depending on the clay deposit, you will be getting some deformation, and that deformation will be solely responsible for the consolidation settlement, right. So, now the specimens are usually 64 millimeter. So, these are all standards. So, specimens are usually 64 millimeter in diameter and 25 millimeter thick, right. Thick means the depth or the height. So, load is applied on the specimen, as I told you, externally applied load will be applied. The specimen is kept under water during the test, it will be completely submerged. That means, you are considering completely saturated condition. So, whatever water will be coming out from the soil matrix. So, there will be no change in say air voids or something like that, right. So, whatever volume change you are getting, that is due to the expulsion of water. each load is usually kept for 24 hours. So, this is pretty time consuming experiment. So, you apply the first load and you wait for 24 hours to deform, because you have to consider 0 to t equal to 0 to infinity, right. So, infinity is so called is 24 hours almost. So, after that you will be getting complete dissipation of say pore water pressure, and whatever enhancement you will be getting, that will be happening in the effective stress, right. So, after that the load is usually doubled. So, that means whatever load you applied initially, now you are doubling the load, and then you observe the same thing, that how much will be the deformation. You wait for another 24 hours and then you see. So, now you will be getting a plot like this, this is the time deformation plot. Now, you see the deformation is plotted on the y axis and time is plotted on the x axis, that is semi log plot. Okay. In this plot you are seeing that you are getting some S curve, right, some nonlinear curve. So, S type of curve. So, in stage 1 basically that is nothing but your initial compression. So, you apply the load, okay. Immediately after that you will be observing some initial deformation or the initial compression, right. So, that already we have discussed, right. Now, in the stage 2 basically this is nothing but your primary concentration. At that period basically your water is draining out. At the initial compression your water will not get enough time to drain out from the soil matrix. Whereas, in stage 2 when the primary consolidation is happening, that means you are allowing the water to drain out from the soil matrix. So, that means the whatever deformation you are getting, that is due to the change in void volume. Okay. In the stage 3 basically this is you are getting secondary consolidation. Even after t is equal to infinity or 24 hours, still you will be getting some amount of settlement, though that is not very significant amount, but you will be getting still some deformation in the soil matrix, because you will be getting some reorientation of the or the plastic orientation of the matrix. So, I mean soil fabrics. So, we will see that. So, stage 1 initial compression, which is caused mostly by preloading. So, immediately you apply the load, you will be getting the initial compression. In stage 2 this is the primary consolidation, during which excess pore water pressure is gradually transferred into effective stress, as we have discussed so far. And in stage 3 secondary consolidation, when some deformation of the specimen takes place because of the plastic readjustment of soil fabrics. So, that means you whatever soil fabrics or the soil particles you have, though you will be getting some plastic readjustment, that means that will not come back again, right. So, due to that you will be getting some secondary consolidation. Now, we will be seeing some void ratio, we will be trying to plot the void ratio versus pressure plot. So, void ratio, we are talking about void ratio because the volume change, whatever volume change you are observing in the consolidation phenomena, that volume change is solely attributed to the void ratio, I mean the change in void ratio, right, because you do not have any change in the volume of soil solids, because soil solids is fixed, the volume of soil solids is fixed. So, you can only play with the volume of voids. So, if you play with the volume of voids, obviously that will ultimately reflect to the change in void ratio. So, we will just plot the void ratio versus pressure, and so that we can see that how the I mean void ratio will be getting reduced with the increase in pressure. So, let us try to first develop or establish the relation, and then we will be plotting them. So, it is necessary to study the change in void ratio of the specimen with pressure, because it is very important, because that will give you that how much change in volume is happening, right, in the matrix. So, ultimately you can correlate that thing with the settlement of the soil, consolidation settlement, and that is very important for designing any kind of structure, because you want to know that how much your foundation will settle due to consolidation. Okay. Okay. So, the first one, calculate the height of solids, that is HS. So, HS is nothing but weight of solid divided by the volume, as well as this is, so I mean A is the cross sectional area, GS is the specific gravity of soil solid, and gamma W is your unit weight of water. So, A into Hs is nothing but the volume of solid, right, and Gs into gamma W will give you the unit weight of solids. So, Ws by A into Gs into gamma W will ultimately give you Hs. Okay. So, we can write further Ms by A into Gs into rho W, where Ms is the mass of soil solids and A, as I told you, it is the cross sectional area. Okay. So, now in the second step, calculate the initial height of voids as, so initial height of voids, that means before applying the load what was the volume of, I mean height of voids. So, height of voids is nothing but the volume of voids, am I right, because as I told you, you have the lateral confinement. So, if you say some volume is getting changed, that change is solely due to the change in the height, not in the radial direction, because radial direction you do not have any deformation, it is completely confined through the ring, am I right. So, calculate the initial height of voids as Hv, okay, that is the initial height, is equal to H, that is the initial height of specimen, okay, minus Hs. It is as simple as that, because Hs is nothing but the height of solids and initial height of the specimen. Say if I have, this is my say specimen, okay, and this is my say height of voids and this is my height of solids and this is the total height, initial height of the specimen. So, Hv is nothing but H minus Hs. Okay. Now, in the third step, calculate the initial void ratio E naught. So, initial void ratio when we are talking about, so that is nothing but Vv by Vs. So, Vs is not going to change. So, when you are considering some soil deposit, Vs is not going to change. So, that is the constant part. So, volume of solid you cannot change it. Okay. You can only play with the volume of voids. Okay. So, E naught is equal to Vv by Vs. What is Vv? Vv is the initial volume of voids. What is that? Hv into A. Hv we have calculated in the second step, right, just now. So, Hv into A is nothing but the Vv, whereas Hs into A is nothing but Vs, am I right. So, from this we can get E naught is equal to Hv by Hs. Okay. So, your volume of voids by volume of solid is nothing but your void ratio. Now, it is equal to your height of voids divided by height of solid, because you do not have any deformation in the lateral direction or the radial direction. So, in the fourth step, for the first incremental loading sigma 1 which causes deformation delta H1, calculate the change in void ratio. So, that means now you are, so this whatever we have calculated so far, those are the initial things or the initial parameters. Now, you are applying some incremental loading sigma 1 and due to that you are getting some deformation. Deformation means only in the vertical direction, only in the longitudinal direction, say that is say delta H1, say that is only in the height change or the change in height, right. So, delta H1 you are observing due to the application of externally applied load sigma 1. Therefore, you can calculate the change in void ratio. So, now what will happen once you apply the load? So, I mean pore water pressure will be, I mean the pore fluid will be getting dissipated and ultimately you will be getting some reduction in volume or the change in volume, and which is basically due to the change in void ratio. So, the delta E1, that is nothing but the change in void ratio, will be equal to delta H1 by Hs, right. So, Hs was your volume of solid. So, the change in void ratio is nothing but delta H1 by Hs, okay. So, from the definition itself. So, it is important to note that at the end of consolidation, total stress sigma 1 is equal to the effective stress sigma 1 prime, already we have seen, right. So, ultimately at t equal to infinity, your effective stress must be equal to total stress, because you do not have any pore water pressure which is getting built up in the matrix, okay, because the whole I mean stressed or the pressurized water will be going out or the draining out from the soil matrix. Now, in the fifth step, calculate the new void ratio after consolidation caused by the pressure increment. So, therefore, E naught was your initial void ratio, and after your application of sigma 1 you have got some change in void ratio delta U 1. So, E naught minus delta U 1 is nothing but your changed void ratio or the new void ratio after application of your externally applied load or the load intensity sigma 1. Okay. Now, for the next loading sigma 2, which causes additional deformation delta H 2. Okay. So, what is the thing? Initially you have some parameters, now you have applied sigma 1 and you have observed some deformation or the change in height as delta H 1, and because of that you have got the change in void ratio as delta U 1. Now, after that, and then you have allowed some t equal to infinity, I mean so called say 24 hours or whatever, and then you are going for the next increment of load, which is say sigma 2. Because of that you are observing some change in height is delta H 2. So, the void ratio at the end of consolidation. So, every time we are considering end of consolidation means t equal to infinity, that means starting point is 0, t equal to 0, and gradually pore water pressure will be getting dissipated and you will be reaching where your total stress is equal to effective stress. That condition we are considering. Okay. So, the void ratio at the end of consolidation will be E 2 is nothing but what was the initial void ratio before starting of the second cycle? E 1, right. So, E 1 minus delta H 2 by H s, that is nothing but your delta E 2, am I right. So, E 2 is equal to E 1 minus delta H 2 by H s. Now, at this time sigma 2 equal to sigma 2 prime, it is obvious, right. We are considering at the end of consolidation, that means the total stress is getting converted to the effective stress and the pore water pressure is simply equal to 0 because of the draining out of the water. Now, the effective stress sigma prime and the corresponding E at the end of consolidation are plotted on semi log graph paper. Okay. So, what we are getting? We are getting the a range of or a bunch of say sigma prime, that is the effective stress. So, we are going on increasing the effective stress. So, effective stress is nothing but the total stress, because at the end of the consolidation we are considering the pore water pressure is 0. So, we are increasing the effective stress, and because of the increase in the effective stress we are getting some decrease in the void ratio. So, we can get a bunch of void ratio values and a bunch of and corresponding a bunch of pressure values or the effective stress values, and then we can plot that thing in a semi log plot. So, I will stop here today. So, in the next lecture we will be continuing this thing. I hope you are enjoying this thing, because this chapter is very important and very say fundamental concept is required to understand this thing. So, please be careful when you will be talking about different parameters and when you will be defining different parameters. Try to understand each and every concept. Okay. So, thank you very much. I will stop here today.